Okay, here's example 4. So we're going to start the same way. So we start with our hypotheses. So it says there are supposed to be 20% orange M&Ms. Suppose a bag of 122 has only 21 orange ones. Does this contradict the company's claim? So I start with my null hypothesis and my alternative hypothesis. So you look for the population proportion. So since there's supposed to be 20% orange M&Ms, that's my population. So my null hypothesis is P equals 0.2. Now, even though this says suppose a bag has only this many, it doesn't state that, we're looking to see if there's less than the 20% or more than the 20%. It just says, does it contradict? So if it doesn't state which side to shade, basically, if it's less than or greater than, we use not equal to. So we're checking to see if our sample contradicts the idea that there should be 20% orange M&Ms. So now my condition. So independence So M&M colors should be independent, but getting one orange M&M has no effect on another orange M&M. Then randomization. This one, it does not state that it's random. So remember, I say not random. But the 122 M&Ms, so we always use our entire sample. So 122 M&Ms should be, so are representative of all M&Ms. The 10% condition, so 122 M&Ms is definitely less than 10% of all M&Ms. And then our success failure condition. So I go ahead and I do n times p. So my n is 122 and my p is 0.2. So I always use the population if I have it. So that gives me 24.4. So that is greater than or equal to 10. And then NQ would be 122 times 0.8, which is 97.6, which is also greater than or equal to 10. So I would say my conditions are met. So I can use a normal model to perform a 1 proportion z-test. Okay, so now my mechanics. So again, I need my n, I need my p hat, I need my p, and I need my standard deviation of p hat. So my n is 122. My p hat, it says that there's 21 orange M&Ms. So 21 divided by 122 is about 0.172. The p is obviously 0.2. And then the standard deviation, remember I'm using the 0.2 and the then 0.8 for Q. So whenever you have the population, you use it. So 0.2 times 0.8 divided by 122, and then I take the square root. So when I do that, I get 0.036. So now I'm going to draw my normal model. So here's my normal model. My mean is 0.2, that's the population, and my sample was 0.172. Now here's what you have to be careful of. This is a two-tailed test. So what that means is I need shading on both sides. The whole idea is if you get a sample like 0.172, you could get that to happen on the other side also. So from 0.172 to 0.2, it's about 0.028 away from each other. So it's saying that you could go 0.028 away on the other side. So I can add 0.028 and get 0.228. So this is my two tails. The not equal to, it's got to have two sides to it. So now what I need to do is I need to figure out the area underneath the curve for both of these, for 0.172 and 0.228. So I don't want you to write this down yet, I just want you to watch. So I would need to find my z-scores. So I have 0.172, I'll do the lower tail first, minus 0.2 divided by 0.036. And I get negative 0.77. Now if I do 0.228 minus 0.2 divided by 0.036, I get positive 0.77. Notice how the z-scores are the same except one's a positive, one's a negative. They're opposite of each other. That's because, remember, the normal model is symmetric. So I'm going the same amount away, just one above the mean and one below the mean. So if I were to do normal CDF for this to get the p-value, so doing z is less than negative 0.77, so I would put in normal CDF, I'd use negative 1,000, my upper bound would be negative 0.77, I get 0.22. If I were to do the same thing for my upper bound, so to do it on the other side, I would be finding the probability that z is greater than positive 0.77. So when I plugged in normal CDF, I'd be doing 0.228, or sorry, 0.77, the z-score for my lower bound, comma 1,000. I get 0.22. What do you notice? Oh, the area under the curve is the same. So for two-tailed tests, instead of doing all of this work for both of these, what you can do instead, erase this, make it bigger. What you can do instead is just find one z-score and one p-value, but multiply it by 2, double it, because you've got two sides now instead of one. So if I were doing this for real, I would pick the 0.172 because, or now I am doing it for real, but I would pick the 172 because that's what I got as my p-hat. And I'm going to find the probability that p-hat does not equal 0.172. So what I'm going to do instead is find 2 times the probability that my z-score is less than negative 0.77. So instead of actually writing it out twice and, figuring everything out, I'm just going to do it this way. So I'd be taking 2 times 0.22, which is 0.44. So my p-value is 0.44. So what it's saying is if the company's claim, if there were truly 20% orange M&Ms, we would get a sample like we did 44% of the time. So I think that the claim that there's 20% M&Ms is pretty accurate. If there were 21 orange M&Ms, if I could get 21 orange M&Ms 44% of the time, I don't think that I've contradicted the company's claim. So I need to write a conclusion. So I would say my p-value is high, and I always include what the p-value is, so 0.44. So we don't accept the null hypothesis ever, because in stats we never accept anything. We never say anything for certain. So what I'm going to say is, so I fail to reject the null hypothesis. So since I'm failing to reject the null hypothesis, I'm saying that the 20% claim is okay. So since I'm failing to reject the null hypothesis, I'm going to say there is no evidence. So there is no evidence to suggest that the proportion of orange M&Ms, forgot the N in there, orange M&Ms differs from the company's claim of 20%. So now you might be asking yourself, how do you know when the p-value is high or low? It's just like what I told you guys before. Unless a problem specifically states otherwise, we always use our 5% mark. So, like I said, at 5% things start being unusual. So it would be unusual to get a sample like we did if the proportion were true. Think about the bead example, right? I had you guys do a test first, and you guys got a percent really low. So we said, well, maybe that claim, my population, was wrong. The proportion I gave you, that 12%. This is what this is doing, okay? We're just writing it in a more precise way, a more statistical way. So this is saying, okay, there's a 44% chance that I would get a sample like I did, given that there's 20% orange M&Ms. So that's very likely that would happen. So I'm okay with their claim. I have no problem with it. Okay? So unless it states otherwise, less than 5%, we reject the null hypothesis. This means that there's evidence to suggest that the alternative is true. So what we're testing against, right? There's a null hypothesis and an alternative. If your p-value is above 5%, we fail to reject the null hypothesis. That means that there's no evidence to suggest that the alternative is true. We'll talk about this more tomorrow when I'm in class, but I wanted to get you guys started. So from here, you can either continue working on the packet, work on your guiding notes that are due on Monday, or you can work on your Math Excel. See you guys tomorrow.